Thanks for joining Focused on Physics. Before we begin, be sure to let me know what you think of my channel so far. I have big plans for this channel, and your feedback will help me grow it in the right direction. If you think my content is helpful, please tell your friends and classmates where they can come to get help on physics concepts. If you want to join in on the conversation, visit me on Facebook. The link is in the description below. Well, we finally made it. Today's video is on projectile motion. We've spent the last few videos building up to this point, starting with the kinematic equations. Make sure you watch that episode if you missed it. Don't worry, this video will still be here when you're finished. We'll start this episode with a brief review of the kinematic equations. We'll then move on to properties that you should know, and finally put our new knowledge to the test with an example. This should look familiar. The 5 kinematic equations along with the 5 kinematic variables. You've seen this table in my earlier videos. While these equations are necessary to describe projectile motion, there are still a few key characteristics that we need to go over. In the kinematics focus problem, accelerating trains, I discussed how we needed to use time to link the motion of multiple objects together. This applies to projectile motion as well. Even though today's problem focuses on the motion of one object, we will need to use 2 sets of equations to describe that motion. That's because each dimension is governed by its own set of equations. If we were describing 3-dimensional motion, then a 3rd set of equations might be necessary. However, time is the one parameter that is not spatially dependent. Velocity, displacement, and acceleration are all vectors. They need to point in a direction. Time, however, is a scalar and allows us to work inside each spatial dimension. Simply put, each dimension is independent of the others. This is perhaps easiest to see with an example. A projectile is fired into the air from the top of a 200-meter cliff above a valley. Its initial velocity is 60 meters per second at 60 degrees above the horizontal. Where does the projectile land? Pause the video here if you'd like to work through this on your own. All right. Let's get started. Of course, the first step is to draw a picture. We'll also need this table once again. The projectile, of course, is influenced by gravity. However, gravity always points downward. Remember how each dimension is independent of the others? Well, the vertical acceleration due to gravity does not play a role in the horizontal direction, so we'll write negative 9.8 meters per second squared for the vertical acceleration and 0 for the horizontal. This is true as long as we neglect air resistance. Air resistance is a very interesting topic that we can get into in a future video. We'll need a bit of calculus and differential equations along the way, so subscribe to be the first to know when those videos drop. Let's turn our attention to the displacement. Displacement is the projectile's final position minus its initial position. In the vertical direction, the projectile starts 200 meters high and ends at a height of 0 meters. Thus, the vertical displacement is negative 200 meters. This is not the same as the horizontal displacement. That is what we're trying to determine. Okay, so now that we have acceleration and displacement written down, we need to work out the initial velocities. Luckily, we covered how to break vectors into their component parts in my trig review video. Give that video a watch if you're unsure how to do this. The simplest way to break a vector down is to represent it with a right triangle. We know the vector has an angle of 60 degrees and a magnitude of 60 meters per second. We will call the vertical component of velocity Vy and the horizontal component Vx. From the trig review video, we can use sine and cosine to determine these components. First up, Vy. Plug 60 degrees in for theta and 60 meters per second in for V0. Check to ensure your calculator is in degree mode, then multiply the two together. Vy equals 51.9615 meters per second. If this were my final answer, I would round it to 52 meters per second. However, I like to keep at least 4 decimal places more than I think I need for in-between calculations. Finding Vx is just as straightforward. We use cosine in place of sine, plugging in the same numbers as before. Because cosine of 60 degrees is 1/2, we get 30 meters per second. Let's make room for the table and fill in our findings. Because the acceleration in the horizontal direction is 0, the horizontal velocity does not change. Since velocity does not change, the final velocity is also 30 meters per second. Whew, we've covered a lot of physics so far. Our work has brought us progress though, as we have 3 of the 5 vertical parameters. We know we can use time to jump from vertical to horizontal components, so let's toss out the final velocity and focus on time. It really doesn't make sense to have 2 separate entries here, so let's join them together. That's better. Now, let's look at our options for equations. We want to include time, so that leaves us with 4 equations from which to choose. We need to choose the one equation that neglects the final velocity. This leads us to the second choice. We've seen this one before, but this is the first time the initial velocity is not 0. We'll start by multiplying 1/2 and 9.8, and then rearrange to set equal to 0. At this point, we turn to the quadratic equation to solve. I'll leave out the math here, but let me know if you'd like to see a follow-up video covering the quadratic formula in more detail. For now, we get that time is either -3 or 13.6046 seconds. Well, that -3 doesn't really make any sense. Let's cross it out and stick with a logical choice. Moving that over to the table, we have now linked the 2 spatial dimensions together. Since acceleration is 0, there's only one equation that will describe motion in the horizontal direction. See for yourself. Go back to the list of kinematic equations and let acceleration equal 0. You'll either get v0 equals vf, or the rate equation you see here. Lucky us though, as this is a straightforward plug-and-chug problem. Plug in 30 meters per second and 13.6046 seconds to get the horizontal displacement of 408.138 meters, which will round to 408 meters. And that's it. Stating the solution in English, the projectile lands 408 meters away. Thanks for watching Focused on Physics. If you enjoyed this video, subscribe, hit that notification bell, and give this video a thumbs up. Leave me a comment to request new content for an upcoming video. Until next time, stay focused. Join in on the conversation on Facebook. Link is in the description.